Greetings of the day. The topic of this paper is multilingual text inversion detection using shape context. First, I will introduce the problem statement, that is to identify inversion from scanned images. There are two components to the solution. First is to localize the text using bounding box detection algorithm, then check the inversion of the text. I will extend this idea to multilingual documents later, and then finally, I will show the result and timing analysis as well. We all know that it's common to have anomalies in scanned documents, but anomalies such as rotation angle or skew can be easily detected. For instance, you can just draw a minimum area bounded rectangle along the identified pixels to understand rotation angle. Let's say there is a line in the document. So we can just find a best fit line using Hawk transformation to find out the skew angle. But these techniques will not work in case of inverted images because theta is equal to 0. Also, if there's a rotation of more than 90 degree, either to clockwise or anti-clockwise direction, then there can be unintentional inversion also after doing the rotational skew correction. Moreover, an algorithm which can detect text inversion in one language may not work for another language. This paper proposed inversion detection algorithm based on a mathematical descriptor called shape context, which mathematically encode the shape information. To complete the pipeline, we propose another bounding box algorithm to localize the text and which will feed in the image patch to the inversion detection algorithm. So this is an end-to-end pipeline that can work irrespective of language. To talk about the related work, there's a paper published in JCIS about waterfall technique wherein the total filling capacity of characters is computed. That means the upright character has more filling capacity than an inverted character. But this method will not work for most non-English languages. There is another method called double peak, wherein we will project all the pixels on the y-axis and analyze the peak on the y-axis. But this will not work in case of capital letter or non-English languages. So this is a simplified end-to-end pipeline where we will take the scanned image as input, then we will find the kernel size to dilate, then we do the dilation and find out the bounding box. Then we get the image patch which contains the text, the word. Then we will identify the language, and then we will analyze the pixels inside the bounding box to understand inversion. Firstly, bounding box detection. There are multiple methods available to identify or to localize a text in an image. From a natural scene, we can identify text using methods called yeast or craft, which are deep learning based. But here in this case, we deal with text-only documents, scanned documents. We can use arithmetic methods which can detect the text much more efficiently. You can see on the right-hand side, there's a logarithmic improvement in efficiency for the contour bounding box method, which is our method, compared to yeast or craft. Along the x-axis, it is the log of the elapsed time. So this is the algorithm. First, we will invert the image, then we will remove the lines using Hawk transformation. We will find the number of contours. It will be very high in the beginning because the number of contours will be almost equal to the number of characters in the image. Then we will iterate the kernel size. We will increase it from 3 to n. Then we will do a morphological dilation. We will grow the foreground, and we will find the number of contours. Note that the contour frequency, the number of contours will take a sudden dip when the characters get merged into words. Then we will fit an inverse sigmoid curve at the tail end of the contour graph to identify whether or where the contour is falling, the number of contour frequency is falling. Then we will find the contour using after a dilation with the identified kernel size. Then we will draw the bounding rectangle which corresponds to the bounding rectangle around the word. So this is why we are doing the inverse sigmoid estimation to find the kernel size. You can see the number of contours will fall suddenly when the characters get merged into words. The y-axis shows the number of contours and x-axis kernels. When we increase the number of kernels, the contours are falling significantly. Here you can see the sigmoid curve, a S-shaped curve, which is similar to this one, except that there's a horizontal flip. So to find the horizontal flip, we just take f of minus x and try to fit this function on this curve. That is why we are trying to fit the inverse sigmoid function to understand or to identify the fall so that we can find the kernel size which is required to be dilated to do the character merge into words. So once we find out the word, we can easily find the bounding box. Then we will get the image match and feed it to the inversion detection. So inversion detection hinges on an idea called shape context, which is a mathematical descriptor to represent the shape of a character. It's a log polar histogram bin like this. It will capture the angle and distance. Let's say this character J is inside this log polar histogram. We will do a random sampling of the edge points of J, take one reference point and throw lines to all other n-1 points. So each line will have different theta and different radial distance. That means it will fall into different bins. So that represents the shape of J. To compare it with another shape, we can just compare the log bin histogram. If it is similar to J, then the cost will be minimum. So we can use this idea to find out the best match alphabet. Here, we can have a base image which contains all the alphabets of the language. If it is English, there will be 26 alphabet. And we will compare it with each alphabet. I mean, we can compute the cost. Cost means that the histogram comparison cost, which we can find out using Pearson's chi-square test. We can use this cost. We will minimize the cost to find out the best matching alphabet. Then take the sum of all the cost to find out the best matching word. I mean, whether it is inverted. I mean, we will compare with both inverted and upright image. So if we do a minimization of the sigma, we will find whether it is a inverted image or a upright image. So to do the first we do the bounding box detection, then we apply a canny edge detection to find out the edge images. We will pick n points at random, construct the shape context. We will compare it with the log polar histogram and do a minimum matching cost to find the alphabet. So, and this is the base image in the middle. Top is the upright and bottom is the inverted. We will compare with each alphabet in the base image and will minimize the cost and sum it up. This idea can be used for multilingual as well because the shape context idea hinges on the concept of shape. Even the text bounding box detection is a language agnostic algorithm because the character merge, the dilation based character merge is based on pixel proximity. It will work irrespective of the language. But the kernel size or the threshold value to classify the inversion depends on the language, or it can depend on the kernel size, I mean the font size and all. But these can be dynamically estimated as I explained before. We can extend the same idea to identify the language also. Here you can see the inversion detection working in multilingual documents. On the bottom, note that the shape match score is significantly different between the upright and the inverted image. This is Greek, this is English, and this is Malayalam, a South Indian language. So in all these cases, there is a significant difference in the shape match score between the upright and the inverted image. So to identify the language, what we can do is we can have different base images, each containing all the alphabet of one language. Let's say there are 10 languages, we can have 10 base images. We can find the minimum matching cost from one base image, and for each base image, let's say 10, we will find the minimum matching cost with each of the 10 base images, and we will see which language we are able to minimize the total cost maximum. So that is how we can identify from L languages which is the language of the document. After that, we can do the bounding box detection, and we can do the inversion detection also. As with any method, there are limitations or boundary cases to this method. For instance, if the selected bounding box contains only inverted text, let's say the document is upright, but the bounding box that we selected contains only inverted text, then the entire document can be classified as inverted, it's a highly unlikely case, but it can happen. Or let's say the bounding box contains characters which looks the same even before or after inversion. Let's say I, C, O, D, K, etc. I mean, these words looks the same after inversion also. If the bounding box contains only these words, then it can be misclassified. So in these cases, we need to take more bounding boxes and analyze to understand whether it is really inverted or not. Another boundary case can be like this will work only for textually scanned document and not on natural scenes, because the bounding box algorithm works only on textual. This is the comparison of result, the confusion matrix of shape matrix on the left hand side. We have taken 100 images for test data and 50 upright and 50 inverted. It is classified correctly here, and in PGG 16 Also, it is classified almost right. I mean, our method is almost the same, if not better, in terms of accuracy. In terms of speed, you can see the difference. The total time taken to detect text in shape context is 0.4 seconds only. This includes the time taken for detecting the bounding box and also do the shape context matching. Whereas this method takes much more time. So it's a very efficient way of detecting the inversion. So to conclude, it's a end-to-end pipeline. We can detect the text and also identify the inversion irrespective of the language. It is simple, it is fast, and it is language agnostic. And there's a significant improvement in speed compared to other methods, and there's a nearly 100% accuracy on the test data set. So these are the references. The source code and the dataset are available in the GitHub here. And thank you. If you have any questions, I'm very happy to answer.